All right, the next astronomer we're going to talk about is another Greek. His name is Aristarchus. And Aristarchus lived from 310 to 230 BCE. So he actually lived to be 80 years old, which back then was very, very old. The life expectancy back at that time was only about 50-some years. The average person would only live to be about 50, 55. So living to 80 was very ancient person at the time. Aristarchus actually was kind of a, he was typical of the Greeks. He delved into everything. He was really into geometry. He was into trying to prove things. He actually believed that the Earth went around the sun, but he had no observation that could prove it. But he did do something that was very creative. We're going to look at this one thing he did for astronomy. Because he realized that here's the sun, here's the Earth, right here, and then we have the moon going around the Earth. And he realized when the moon was up here, so that it was exactly half lit. Since the sunlight coming from the sun is what lights up the moon, if it's exactly half lit, if I draw a line to the Earth and I draw a line to the sun, then that has to be a 90-degree angle. And in geometry and trigonometry, we love right triangles. Because once you have right triangles, you get one other angle, you can figure out all the rest of the sizes and distances. And so what he did is he had somebody go out and measure this angle right here. We're going to call this angle theta. And once he knew that, he could get the relative distance between the Earth-Sun distance, right here, this is the Earth-Sun distance, and the Earth-Moon distance. Essentially what he's trying to figure out is how many times further away is the sun than the moon. They already knew the sun was further away, because during a solar eclipse, the moon would pass between it. So the sun had to be much further away than the moon. But they didn't know how much further away it was. So what he did, for those of you that had trigonometry, is he just used a simple trigonometric expression. He said, okay, this is my right triangle. This is the hypotenuse over here. This is one leg. This is the other leg. In fact, what we're going to do is we're going to do it the way they do it in trigonometry. This is the adjacent. This is the opposite. So this angle here, if I take the cosine of the angle, it's equal to the adjacent over the hypotenuse. And then if I measure that angle, which he had people go out and measure that angle between the sun and the moon, because you can see them both in the same sky, then he could calculate this ratio. You take the cosine of that, you figure out what that ratio is. And so he calculated the ratio of the distance to the moon to the distance of the Earth, and he got that the sun, the distance of the moon relative to the distance of the sun is about 20 times. Or essentially he calculated that the sun was 20 times further away than the moon was. Now this was not even close to being accurate, because the real answer, this is what Aristarchus got, the real value is about 400. So the sun is 400 times further away than the moon, but surface-wise it's 400 times bigger, so that actually makes them match up to be the same size in our sky. Now, to give Aristarchus credit, it wasn't his technique that made him mess up so much, miss by a factor of 20. It was because this angle is really, really hard to measure. This angle is very, very close to 90 because the sun is so far away relative to the moon. At the time, they couldn't imagine that the solar system was that big as it was, the relative distances. And so measuring that angle was tough because this angle was like 89.6 degrees, and that's really tough to do when it's close to 90 degrees. And if you're off by any at all, it's going to make a significant difference in what your value is. So, what I want you to know about Aristarchus is he calculated, or he determined a method to get the relative distance of the sun compared to the moon. or he figured out how many times further the sun was away than the moon. All right, that's all we're going to do with Aristarchus. We're moving on to another Greek. And this Greek was named Eratosthenes. And Eratosthenes did something very important. First of all, he lived from 276 to 195 BCE. Remember, this is the height of the Greek Empire. All right, this was when they had expanded and they had pretty much taken over most of the place around the Mediterranean Sea. Now remember Alexander, who was actually a student of Aristotle. Alexander the Great, he took his army and went all the way to India, conquering as he went, and then he died on the way back. He died very young. But Eratosthenes was a librarian at the Library of Alexandria. Remember I told you about the Library of Alexandria? The idea of the Library of Alexandria was to collect all the works of the world, and somebody had to try to organize this. I mean, we're talking 1 million scrolls at least. There may have been even closer to 2 million. Nobody's quite exactly sure. But you had to have librarians to organize this. Well, Eratosthenes was one of these librarians. And it's kind of funny because even back in the time of ancient Greek, people made fun of the librarians. The scientists, the philosophers, would make fun of the librarians. In fact, they called Eratosthenes Beta. That was his nickname. Well, you got to remember the Greek alphabet goes alpha, beta, gamma, delta, meaning that Eratosthenes was always second in everything. He was never the first to do anything. So they were kind of mocking him by calling him that. But Eratosthenes did something that we remember him by. We don't remember the other people by, because he did something very profound. He was reading a scroll, one of the scrolls that he was organizing, and he read that in the town of Syene on one day of the year, light would go to the bottom of a well. And, you know, most people go, oh, that's interesting. That's an interesting fact. But Eratosthenes, it clicked. He realized, you know what? If I know that the light goes to the bottom of the well, that means the sun has to be directly overhead on that day of the year. And if I know how far it is from being overhead at some place north or south of there, I can figure out the size of the Earth. That's what Eratosthenes did, is he figured out how big the Earth was. Remember, Aristotle already told us it was spherical, but nobody was sure how big the sphere was. All right, so what he did is this. So here's our Earth. Okay? So here is a well in Syene. On this particular day of the year, sunlight goes all the way to the bottom of the well, which means the sun had to be directly overhead. Okay? Now, by this point, they knew the sun was so far away that its light rays pretty much just come in parallel. So all the light rays coming from the sun are coming parallel for anywhere on the Earth. And he said, okay, if that's true, if I have a flagpole up here, here's my flagpole, in Alexandria, which is where he was at, the flagpole is made so it points straight down too. So I can extend these backwards, the well and the flagpole, and they meet at the center of the Earth. Okay? And if I just measure this, so here's my line here, here's sunlight coming in. If I measure this angle, which is easy, that's just the angle of the shadow. How big is the shadow here on the Earth? Remember, this just makes a right triangle. He measures this angle. That angle has to be the same as this angle. That one and this one are the same. These are alternate interior angles of parallel lines. Remember back to taking geometry in high school. So, if you could measure that angle, you would know this angle, and if you knew the distance here, the arc length, you could figure out the size of the Earth. And so he did it. He measured the angle, and he found that the angle on that day in Alexandria, this angle right here, was 7 degrees. Then all he had to say was, oh, well, 7 degrees is to 360 degrees, meaning we're making a radial. This is to the whole circle, the same as the distance here, we're going to call this d, is to the circumference of the Earth. So all he had to do, he knew this, if he could find that, he could figure out how big the Earth was. So what did he do? He hired a guy. He hired a guy that had a known walking pace. He could walk at exactly a certain number of steps. He counted all the steps. He walked all the way from Alexandria to Syene, counting how many steps it took to figure out how big the Earth was. What he got was that the distance from Alexandria to Syene was 5,000 stadia. So this is what he set up. He said, oh, this is going to be equal to 5,000 over c, which is the circumference of the Earth. And this is in stadia. Well, if you calculate this, you get c is equal to, very easy, 257,000 stadia. All right, so remember I told you that in Columbus's day, Columbus was arguing the Earth was smaller